afternoon, ladies and gentlemen. I would like to talk about my work, about geometry of deformed black holes, and especially about superpositions of black holes with another source of gravity. At first, I would like to show a superpositions which called Majumdar-Papapetrov solution. It's a superpositions of many extremely charged black holes, and the rest of my talk is focused on Schwarzschild black holes surrounded by a Bach-Ware ring. I will talk about analytic expressions of the matrix and show you how the matrix functions looks near horizon and near the singularity. And finally, I will show you some pictures of invariants which we are calculate inside the black holes. This presentation is made pursuant to diploma thesis, geometry inside deformed black holes, and the paper which I worked together with Professor Oldřich Semerák from Institute of Theoretical Physics in Prague on geometry of deformed black holes. So let's start with Majumdar-Papapetrov solutions. The matrix in general is here, follow. It's really simple. We have only one metric functions U for many extremely charged black holes, which is at Ri, as we can see in this expression of U, and the U is quite similar to classical potential of spherical sources, as we can see. From now, let's consider two extremely charged black holes, the binary system, which we can rewrite into this simple form. And as we can see, the matrix show only the horizons of the black holes at the R is equal to 0. And the way how we can describe the matrix below horizon is by choosing negative R. And this way how to show the area below the horizon is actually done at Chandrasekhar's work at his book The Mathematical Theory of Black Holes from 1983. At first, we can show the horizons are perfect spheres by these calculations. The first one is the area of the horizon. We can see the area corresponds to the sphere with radius m, and this second and the third calculations is the length of the meridian starts from pole to some point at coordinate theta, and the last calculation is length of the equator which starts around coordinate theta. And as we can see, the results perfectly fit to the sphere of radius m. This is just one of the most ways how to describe the geometry of horizon by this length and areas. And for now, let's see how the space-time looks below horizon and outside of the horizon. The left picture is a situation outside of the horizon. We have two black holes here. The second one is 2.5 massively than the first one. The b is the parameter of the distance. The first of the black holes is here on the left and the second is on the right. And the second picture on the right is the situation below horizon. We use a little different coordinate than Chandrasekhar, r, which is equal m plus r, just because there's a little more obviously that the horizon is perfect sphere, and the red line here is a singularity, physical singularity. The physical singularity is actually point-like, but this is the just effect of using coordinates. Here we calculate another scalar, the Ricci square scalar, for our case of two extremely charged black holes. We can see at the picture there is a little area of zero value of this scalar, which is corresponds to point where the tensor of electromagnetic field vanish. And the last scalar is a Kretschmann scalar for our two extremely charged black holes. As we can see on all these pictures, especially at the right side below horizon, there is not many changes in the ways of invariance. So we can ask if the horizon is the perfectly sphere which is independent on the another source of gravity. We can ask if it's possible that there is no effect of outer black holes into whole region below horizon. And for spherical, so let me explain that if there is no effect of the outer source to the area below the horizon, so we need to have a spherical symmetry below the horizons of the black holes, as in the case of whole right-hand Nordstrom extremely charged black hole. Yes, and the condition of this spherical symmetry, one of the conditions of spherical symmetry below the horizon is that the invariance, the level of the invariance is not intersect together, because all the levels need to be perfect sphere. It's not easy to see on this picture when we plotted the levels of the constant value of the invariant, the intersecting, but we can calculate this condition analytically by the equation on the right side. For the intersection of the levels of constant value, we need to this equation equal to 0, and we can show for any invariance, for example k and u, just choose any of them, this equation is not equal to 0. Actually, the expression is quite complicated for this short presentation, but still we can prove that analytically that this condition is not equal to 0, which indicates there is no spherical symmetry below the horizon in this solution. So this was just a little journey into Majumdar-Papapetrov solutions, and for next, let's see the second studied space-time, the Schwarzschild black hole surrounded by Bach-Weil ring. Bach-Weil ring is a statically spread mass intercycle, which is chargeless, and it indicates the space-time with this type of ring is static and axially symmetric space-time. We can write any static and axially symmetric space-time into this simple form, which is called Weil coordinates, and the Einstein equation is presented here. The advantage of this expression is that here we have a combination of linear equations. I can't see the set of the linear equations because there is a nonlinearity at new function at the last equations, but still we can solve the first equations and found a new function, and after this calculation we can use a new as a right side into another equations, and in the second round we have also linear equations with something on the right side. So due to this linearity we can calculate the new function of two known sources by this simple sum. But in order to this nonlinearity, we cannot do the same work with the lambda coefficient, and I need to calculate it separately. And here is the solutions for our objects. The first, the Schwarzschild black holes, and the second, the Bach-Weil ring. The lambda function for the Bach-Weil ring is also known, but actually we don't need them because we need to calculate the superpositions separately. For superposition, it's more comfortable to use another type of coordinates. The transformation between y coordinates and r, the Schwarzschild coordinates, is here, and the matrix looks similar to Schwarzschild space-time, but we have a new exterior and lambda exterior, which is defined by this, the nu of Bach-Weil ring, and also there is a lambda exterior. And the question is the extension of the matrix below horizon defined correctly by this matrix? And the answer is no, because there is no problem with any parts of the matrix, and the only problem is at the knee exterior. If you look at the transformation, so by choosing r between 0 and 2m, we obtain a pure imaginary row. And we can ask if the new exterior is defined correctly for imaginary values, and the answer is simply not. But we can correct these extensions to another form, which has no problem with pure imaginary row. This is one of the way how obtain the new nu for area below the horizon. Is more complicated, but it has no problem with convergent at the area below the horizon. And one of the most important facts in this matrix is that the matrix function near horizon and singularity is really simple. We can calculate it analytically by this formula, and for our case of Bach-Weil ring, there is a simple result at the last line. And one of the results also that the singularity of black holes is still point-like if we have a presence of Bach-Weyl ring. And for now, here we have Lux functions for two different rings with different distances. The black line is the horizon of the black hole, of Schwarzschild black hole. The physical singularity is at 0 point, and the red line on the right picture is just border when we need to use a new expression of the new function. As I told before, the new function has a problem with pure imaginary row at some areas. So for the near ring with small b, we need to use our new functions for calculate invariance at all parts below the horizon. And for now, here we have a gravitational acceleration invariant. It's negative at some areas. The red areas indicates negative values of this invariant. We actually plotted the square of this invariant, but we should know that the scalar product is not positive definite in general relativity, so there is not so miracle that some square invariant is negative. And the last